Hello everyone. So let us continue our discussion. We are in week 12 and this is our fourth lecture, right? So what we have studied now is the Euler's buckling load, right? Now, if we have say three different columns, one as you can see on your screen, then another one here, the third one we'll draw in a minute, but for the time being, you can see the first one is a very short one. We have already defined the short column and long column. So if we apply P on this column and if the cross-sectional area is say A, so obviously sigma is P by A. And for this column, if the slenderness ratio, if you recall slenderness ratio, say lambda is equal to L effective divided by R, right? So we'll revisit this again in a minute. But if we have slenderness ratio small, then we have a short column and this one fails under crushing. Well, the one on the right hand side, you see if we apply a load P, and because this is a long column where we have L effective much bigger, or in other words, the slenderness ratio is bigger than the one we have here. For this column, we have critical load, which is pi square EI divided by L effective square. Now I is equal to AR square. So we have here pi square EA, and then we can write L effective divided by R whole square, right? So effectively we have pi square EA divided by lambda bar square. Now, this column, which is a long column, it fails due to buckling, right? Obviously, there is an intermediate stage where both crushing and buckling acts together, and this is an intermediate column. Now, here if we apply say P, then obviously it will have the combined effect of what we can see on the left and what we can see on the right. Now, effectively what we have is a situation where we have P crushing, say PC is equal to sigma C times cross-sectional area. And then P critical, CR, is equal to pi square EA divided by lambda bar square. And somewhere in between we have a combination of both of them, and to address this issue, Rankine proposed an empirical formula, so that is called Rankine's empirical formula. And as per this empirical formula, 1 by P is equal to 1 by PC plus 1 by PCR. So the first component, PC, it is constant for a given material and cross section. While this P critical depends on lambda. Now, before we move further, if I draw the critical load versus lambda plot, so on the y-axis we have critical load and lambda bar, that is the slenderness ratio along x-axis. So we get a plot like this. So lambda bar is equal to L effective divided by R. Now, for a given cross section, if you increase L effective, obviously in this expression, which is pi square EI by L effective square. So in this formula, if we increase L effective, obviously P critical is reduced. As you can see from this graph. On the other hand, if we reduce L effective, P critical increases, as you can see from this dotted line, right? Okay. Now, for Rankine, we have 1 by P, that is the Rankine's critical load. So let us call it, say, PR is equal to 1 by PC plus 1 by PCL. Now, in a case, if we have pre-critical dominance, that means slenderness ratio is very high, then for that column, obviously this part will not be considered, right? Now let us put the expression of PC and PCR and let us see what we get. But before that, we have P Rankine is equal to PC times PCR divided by PC plus PCR. Or in other words, we have PC divided by 1 plus PC divided by PCR. Now we can put the expression of PC and PCR. Let us do that. What we have in the numerator, we have sigma C times A divided by 1 plus, we have sigma C times A divided by pi square E A R square divided by L effective square. So therefore, we have P Rankine is equal to sigma C times A divided by 1 plus, we have sigma C times this A will get cancelled and we have L effective square divided by pi square E times square. So E effective by R is the slenderness ratio. Then we can further simplify this expression. So we have PR, which is sigma C times A divided by 1 plus, we have sigma C times lambda bar square. So sigma C times lambda bar square divided by, we have pi square E. Now, let us look at this expression sigma c divided by pi square E. See, the unit of sigma c is force per area square, and we have the same unit of Young's modulus. So this is a non-dimensional number, and let this be alpha. So effectively what we get Pc divided by 1 plus alpha times lambda bar square. Now again, lambda bar is equal to L effective divided by R. So it is again dimensionless. So effectively what we have 1 by 1 plus alpha times lambda bar square times Pc. So effectively what we get, Rankine's critical load PR is equal to some constant times Pc. So that is the crushing load acting on a column. So Pc is equal to sigma c, that depends on the material, times the cross-sectional area. So if we find out the compression capacity of the column, then if we multiply that with a factor, then we can take care of the effect of buckling that is modeled by Euler's buckling formula, and we get this expression for critical load as per Rankine. Now, as I have already explained, that if you look at the first expression of Rankine's formula, which is here, so it has the effect of crushing that comes from the first part and the effect of buckling that comes from the second part. Now, in a case where buckling dominates, obviously the first part will not be significant, and vice versa. And for an intermediate column where we have combined effect of crushing and buckling, we can use this Rankine's formula. And the advantage of this Rankine's formula is what is shown here, that you evaluate the compressive strength of the column Pc from the material property sigma c and the cross-sectional area, and then multiply that by a factor which is normally recommended in the code. It is 1 by 1 plus alpha times lambda bar square. So from the geometry, we can find out lambda bar, that is the slenderness ratio of the column. Okay, and then we can also find out this alpha. It depends on the material property, you see sigma c and the Young's modulus of the material. So we can easily find out the alpha, and we can find out this kappa parameter, and if you multiply that non-dimensional parameter kappa with Pc, we get the Rankine's buckling load. And obviously in this Rankine's expression, it has the effect of both crushing and buckling, but we estimate it from the crushing load only, and in this non-dimensional kappa value, the effect of buckling is embedded. So let us take an example and see how this works. So example 1. In this example, we have a column of length 4.5 meter. It has a hollow circular cross section. So D, outer diameter, is 200 millimeter, and the thickness of the wall is 25 millimeter. Then E is equal to 2.1 into 10 to the power 5 Newton per millimeter square. Then sigma C is equal to 550 Newton per millimeter square. Our task is to compare Euler's critical load with Rankine's critical load. Okay, so for this problem, let us first find out I, and boundary condition is hinge. So both ends of the column are hinged, and for that, let us first find out Euler's critical buckling load, and then we'll find out Rankine's critical load. So moment of inertia for this hollow circular cross section is pi by 64 times d to the power 4 minus small d to the power 4. So effectively we have pi by 64, capital D is 200 millimeter, so 0.2 to the power 4 minus small d is 200 minus 2 into 25, so this is 150 millimeter. So we have here 0.15. So if we evaluate, we get moment of inertia is 5.37 into 10 to the power minus 5 meter to the power 4. Now we can find out critical load. So P critical Euler is equal to pi square EI divided by L square, which is equal to pi square times 2.1 into 10 to the power 11 times I is 5.37 into 10 to the power minus 5 divided by length of the column is 4.5, so it is 4.5 square. Now if you evaluate this, we get 5495 kilonewton. So the first part is evaluated, that is the Euler's critical buckling load. Now we have to evaluate the second part, and for that let us first estimate PC, that is the crushing strength of the column. So sigma C is 550 times cross sectional area, it is a hollow circular cross section, so pi by 4 times D, which is 0.2 to the power 2 minus 0.15 square. Now the value of PC is 7559 kilonewton. Okay. Now we can evaluate P critical Rankine, which is PC times P critical Euler divided by PC plus P critical. So if we put the expression, we have 7559 times Euler's critical load, which is 5495. So 5495 divided by 7559 plus 54. So the Euler's critical load is 3182 kilonewton. Now, if we find out the ratio of P critical Rankine and P critical Euler, we have 1:1.73. Right. So now we can see how we can combine the crushing strength under pure compression and the buckling, and we can evaluate the critical load as per Rankine's empirical formula. And the advantage is, normally in the design codes this expression is given, and where we find out PC and multiply that with a factor, you can see here, and then we can get the effect of buckling, and we get the combined effect which is embedded in the Rankine's empirical expression. This is very useful in the design, and as you progress in your undergraduate course, the design course will actually use this expression, and you're going to design the column accordingly. So you'll see that the code refers this expression, and it reduces the workload, because from the compressive strength of the column PC, we can directly find out the Rankine's critical load, right? So let us close here. In our next class, we will see further how we can model the buckling of column.
If you have any doubt, please drop a mail to us, then we will clear your doubt. Thank you very much.